Hello. If you missed the lesson on Workbook 20, you are in for a treat because I'm going to go through it rather fast and do the workbook with you. So buckle up. And this is, you should have only gotten this by request, or if it's been long enough, I might just put it up. You might be able to hear my lovely assistant in the background as we are working. So I apologize if it sounds a little bit crazy. Okay, dilations. So we have talked about so far rigid transformations. Rigid transformations keep everything the same. So you have the same angles, the same sides, the same shape. It all stays the same. Like it's preserved is what we say. Dilations they preserve only the angles. So like if this was our triangle right here and we dilate it, like the angles, like right there, they're going to stay the same. But the side lengths are obviously going to change. So that is a dilation. And that's basically what you need to know with what a dilation is. And then we have words that we talk about. We have the center of dilation, saying that this is a place where it like grows from. And notice the angles all stay the same. With this particular one, I'm going to say something in just a second. My assistant is having a hard time. The pre-image point is halfway between the image and the center of dilation, meaning that would have to be 2. So then basically saying that rigid transformations versus dilations just mean that they're both going to preserve the shape, just dilations make it bigger or smaller, and by proportionality. So we're just going to look here. This was a dilation. So what was preserved? So the transformation preserved side lengths. It did not. This is a non-rigid transformation because it did not preserve the side lengths. It doesn't preserve the side lengths. It does preserve the angle measures. It is not rigid, and it does preserve the angle measures. So there's that one. Next one. So we're looking at these things. We're going to look at this. So 9.2, 9.5, not the same, not the same. So did it undergo a dilation? No. Because a dilation would mean that you'd multiply it to get something bigger. So looking at this one, so from 6 to 12 multiplied by 2, multiplied by 2, multiplied by 2, and I would say yes, it did. Okay, so that is 20.1, 20.2. I'm going to move my little picture here, 20.2. Is dilating lines, which this one's kind of a weird one. It wants you to dilate a line, which you can't. Like this is such a funny thing. Scale factor, they say is K, and notice like this doesn't do anything because the line technically goes on forever, and you can't stretch a forever line on twice as forever. So I don't know why they're talking about that. Anyway, so then the dilation of a segment, so yes, you can dilate a segment, creates a blank line segment. It would be parallel though, because if you look at the last thing that we did on the last lesson, think about that. So we had like the center dilation, one thing, it went twice as big, and it's right here. The lines were parallel. So that was a really horrible description in the lesson. Now you've got it though. Okay, then choose the phrase that best fills the blank on the following description of dilation. If point B is the center of dilation for line AB, the image of the dilation is B, it is the same as line AB. That's what we're looking for. It's because it's the weird thing. How to keep on going. Okay, then we have 20.3, I think, and then a checkpoint, right? Okay. Let's check. This is 20.3 and then the checkpoint. Good. Okay, so this is actually the meat of dilation. So scale factors and length. So we talked about it being twice as big. So then look at this. So if you were to so this is, if I slide this, watch how that moves that. In fact, I can do negative. So we have a scale factor of 0.7, makes it smaller. If I go bigger than 1, makes it bigger. So if it equaled 1, it's the exact same thing. So the scale factor, if it's bigger than 1, makes it bigger. Less than 1 makes it smaller, but notice it can't go negative. So negative doesn't work. So it has to be between 0 and 1 makes it smaller. Between 1 and above, and then above 1 makes it bigger. That's what you need to know. and it's proportional. So if you divided KL by EF, you would get the scale factor. That's how you can calculate it. And then the ratio of KL to EF is always the same as the scale factor. Okay, and then, so we can do that scale factor thing. Another way to find it is by doing, like, looking at other sides. So the distance from the image up to the center and the distance to the pre-image to the center. So that was like I was saying, there's my cat. That's what I was saying. The thing was twice. I knew that the scale factor was 2 because it was halfway between, meaning that total distance from the center of dilation to the image, and then that pre-image was halfway between, meaning it split it up. So the ratio of the whole thing to the part thing was 2. And so that's why it's doing that thing right there too. I think it's the same thing. We just talked about this. Why is it doing it again? Anyway, so under any dilation, the image is smaller than the pre-image. The scale factor would have to be between 0 and 1. Okay. All right. So then a triangle undergoes a dilation with a scale factor of 9/5. So 9 is bigger than 5, meaning it's bigger than 1. So that means that it's going to be larger than the next one. Okay. Then a graphic is printed on a circular banner, diameter of 4 feet. The same graphic undergoes a dilation with a scale factor of 1/6. The diameter can be the diameter of the dilated graphic is, so then 1/6 of 4. So 4 divided by 6 reduced is 2/3. Okay. That's a happy girl over there. Checkpoint, because might as well put them all together. Oh, I got that one wrong. Oh, snap. Let's check it out. What did I do? It has a diameter of 4 feet. Oh, it was 2/3 of that. So 2/3 feet. But now we need to take that in inches. So 2/3 of a foot would be 8. So I would go back and do that, but for the sake of time, I'm not gonna. So make sure you don't make the same mistake as me, because it was 2/3 of a foot, but 2/3 of a foot is 8 inches, because you do 12 divided by 3 is 4, and 4 times by 2 is 8. Okay, so determine the value that fills in the blank that makes the statement true. Under a dilation with a scale factor of 4/5, so notice that makes it smaller, a 10-inch segment becomes a blank inch segment. So when you multiply, so you're going to have to multiply by the scale factor. You multiply by a fraction, you divide by the bottom and times by the top. So 10 divided by 5, because that's the bottom, or the denominator, is 2. And then 2 times by the numerator, the top, is 8. So that it would be 8. And then a triangle that undergoes a dilation with a scale factor of 7/10. So that's less than 1, because 7 is less than 10. It's going to be smaller than the original triangle. Then a dilation is a transformation that maps every point on a line segment to a point on a parallel line segment. The image has a length that is determined by the pre-image in a scale factor, which is a fixed ratio. A fixed blank of the original length, and multiple, because we have to multiply it. Okay, and then, so to get from the smaller one to the big one, looks to me, all the A's and the A primes and the B and B prime, they all line up. So the only thing that happened was a dilation centered at the origin, because it grew from the origin. Then quadrilateral ABCD is dilated with the center dilation at the origin to make the blue one, which our statements are true. So this is basically asking what happens with the dilation. So it does not preserve side lengths. It is not rigid. It does preserve angles. It's not rigid, and it does not preserve side lengths. Okay, there we go. Now, if I don't get the checkpoint wrong, I need to go back and fix it, but I got it all right. Okay, good. So that was workbook 20 with the checkpoint.